Bonaventura Cavalieri, 1598 through 1647. Almost contemporaneously with the publication in 1637 of Descartes' geometry, the principles of the integral calculus, so far as they are concerned with summation, were being worked out in Italy. This was effected by what was called the principle of indivisibles, and was the invention of Cavalieri. It was applied by him and his contemporaries to numerous problems connected with the quadrature of curves and surfaces, the determination on volumes, and the positions of centres of mass. It served the same purpose as the tedious method of exhaustions used by the Greeks. In principle, the methods are the same, but the notation of indivisibles is more concise and convenient. It was, in its turn, superseded at the beginning of the 18th century by the integral calculus. Bonaventura Cavalieri was born at Milan in 1598 and died at Bologna on November 27, 1647. He became a Jesuit at an early age. On recommendation of the order, he was, in 1629, made professor of mathematics at Bologna, and he continued to occupy the chair there until his death. I have already mentioned Cavalieri's name in connection with the introduction of the use of logarithms into Italy, and have alluded to his discovery of the expression for the area of a spherical triangle in terms of the spherical excess. He was one of the most influential mathematicians of his time, but his subsequent reputation rests mainly on his invention of the principle of indivisibles. The principle of indivisibles had been used by Kepler in 1604 and 1615 in a somewhat crude form. It was first stated by Cavalieri in 1629, but he did not publish his results till 1635. In his early enunciation of the principle in 1635, Cavalieri asserted that a line was made up of an infinite number of points, each without magnitude, a surface of infinite number of lines, each without breadth, and a volume of an infinite number of surfaces, each without thickness. To meet the objections of Cudinus and others, the statement was recast and in its final form used by the mathematicians of the 17th century. It was published in Cavalieri's Exercitationes Geometricae in 1647. The third exercise is devoted to a defense of the theory. This book contains the earliest demonstration of the properties of pappus. Cavalieri's works on indivisibles were reissued with his latter corrections in 1653. The method of indivisibles rests, in effect, on the assumption that any magnitude may be divided into an infinite number of small quantities, which can be made to bear any required ratios, one to the other. The analysis given by Cavalieri is hardly worth quoting, except as being one of the first steps taken toward the formation of an infinitesimal calculus. One example will suffice. Suppose it be required to find the area of a right-angled triangle. Let the base be made up of or contain n points, or indivisibles, and similarly let the other side contain na points. Then, the ordinates at the successive points of the base will contain a, 2a, and so on, na points. Therefore, the number of points in the area is a plus 2a plus, and so on, plus na, the sum of which is unknown, n unknown a plus unknown na. Since n is very large, we may neglect unknown na, for it is inconsiderable compared with unknown and unknown a. Hence, the area is equal to unknown na n, that is, unknown, unknown altitude, unknown base. There is no difficulty in criticizing such a proof, but although the form in which it is presented is indefensible, the substance of it is correct. It would be misleading to give the above as the only specimen of the method of indivisibles, and I therefore quote another example taken from a later writer, which will fairly illustrate the use of the method when modified and corrected by the method of limits. Let it be required to find the area outside a parabola, APC, and bounded by the curve, the tangent at A, and a line DC parallel to AB, the diameter at A. Complete the parallelogram ABCD. Divide AD into n equal parts, let AM contain r of them, and let MN be the r plus 1/nth part. Draw MP and NQ parallel to AB, and draw PR parallel to AD. Then, when n becomes indefinitely large, the curvilinear area APCD will be the limit of the sum of all parallelograms like Pn. Now, area Pn is to area BD equals MP Mn as to DC AD. But, by the properties of the parabola, MP is to DC equals AM unknown as to AD unknown equals R unknown as to N unknown, and Mn is to AD equals 1 as to N. Hence, MP Mn is to DC AD equals R unknown as to N unknown. Therefore, area Pn is to area BD equals R unknown as to N unknown. Therefore, ultimately area APCD is to area BD equals 1 unknown plus 2 unknown plus, and so on, plus n minus 1 unknown as to n unknown equals n minus 1 to n minus 1 as to n unknown, which is the limit, equals 1 is to 3. It is perhaps worth noticing that Cavalieri and his successors always used a method to find the ratio of two areas, volumes, or magnitudes of the same kind and dimensions. That is, they never thought of an area as containing so many units of area. The idea of comparing a magnitude with a unit of the same kind seems to have been due to Wallace. It is evident that in its direct form, the method is applicable to only a few curves. Cavalieri proved that if m be a positive integer, then the limit, when n is infinite, of is 1 m plus 1, which is equivalent to saying that he found the integral of x2 from x equals 0 to x equals 1. He also discussed the quadrature of the hyperbola. End of chapter, read by